As image data continues to grow, the demand for efficient compression with high perceptual quality has become increasingly important. Traditional codecs, as well as early neural codecs mainly optimized for PSNR, achieve good rate distortion trade-offs on paper, but tend to produce blurry reconstructions at very low bit rates. To address this, GAN-based generative codecs were introduced. These methods synthesize high-frequency details, improving perceptual realism. However, when pushed to extremely low bit rates, they often introduce distortions and cannot maintain faithful reconstruction. Recently, the field has shifted toward generative tokenizers. These models leverage strong generative priors and have achieved impressive perceptual quality under extreme compression. Yet they still face fundamental challenges, which leads us to our problem definition. A generative tokenizer maps image patches into discrete codebook entries, clustering similar visual patterns into compact tokens that can be decoded by a powerful generator. Such tokenizers are effective at clustering dataset-level semantics, which helps to capture common structures efficiently. However, because the codebook is finite, they inevitably sacrifice object-level details when operating at very low bit rates. As a result, while generative tokenizers deliver strong perceptual realism, they remain suboptimal for tasks that demand reconstruction fidelity under extreme compression. This motivates us to rethink the bottleneck design. Our solution is called Dual-generative latent fusion, or DLF. The key idea is to split the compressed representation into two complementary parts, one for semantic content and another for fine details. The semantic branch leverages the clustering power of generative tokenizers, which efficiently capture dataset-level contents and compress them into compact tokens to save bits. The detail branch, on the other hand, focuses on object-level fidelity, encoding diverse details in a more flexible quantization space. To make these two streams work together, we introduce a cross-branch interaction mechanism. This component reduces redundancy between the branches and ensures that bits are allocated where they are most needed. At a high level, DLF provides a more adaptive and efficient bottleneck than conventional generative tokenizers, enabling both strong perceptual realism and faithful reconstruction at extremely low bit rates. Then is the detailed design. The semantic transform uses a one-dimensional tokenizer to compress each 256 size patch into compact tokens, while the detail transform relies on SwinCon blocks to extract more diverse object-level information. These two branches do not work in isolation. They interact through multiple interactive Tarantrium modules, which reduce redundancy and optimize bit allocation between them. For quantization, the semantic branch adopts vector quantization, which is efficient for clustering common semantics, while the detail branch employs scalar quantization, enabling a much larger quantization space to better represent fine-grained content. Afterward, a latent adapter fuses both streams into the latent space of a pre-trained VQ GAN generator, which produces the final decoded image. On the right, the entropy map illustrates how detail branch allocates more bits adaptively to the regions containing specific details. Red solid boxes are details of specific objects which consume more bits. Dashed yellow boxes are relatively more common contents, which require fewer bits despite having high-frequency information. More architectural details, such as the exact block structures and training strategy, can be found in our paper. Next, we turn to the qualitative evaluation. At the lowest bitrate, our method consistently delivers the most faithful visual quality, preserving fine details that competing approaches fail to reconstruct. These examples clearly demonstrate how DLF achieves both perceptual realism and detail fidelity, even under extreme compression. For additional visual comparisons across different datasets, more results are included in our paper. For the quantitative evaluation, DLF achieves state-of-the-art performance across multiple datasets and perceptual metrics, consistently outperforming prior codecs at extremely low bit rates. In summary, we introduced DLF dual-generative latent fusion for extreme image compression. DLF splits the latent into a semantic stream vector quantized tokens and a detail stream scalar quantized features, coupled by cross-branch interaction to reduce redundancy and allocate bits where they matter most. Across datasets and perceptual metrics, DLF delivers state-of-the-art fidelity at ultra-low bit rates and decodes more efficiently than diffusion-based codecs.